Okay, so our next session is going to be focused on tsunami generation and inundation. This session will discuss new research focused on tsunami simulations from the Cascadia Subduction Zone and crustal faults, as well as tsunami debris forecasting and tsunami evacuation. So our first speaker and actually I do want to mention, just in case there's any folks that are joining us late, speakers, you'll get we'll give you a 30-second warning. So when you get to the 4-minute and 30-second mark, Karina will let you know that you have 30 seconds left. And our first speaker today is going to be Carrie Garrison Laney with Washington Sea Grant and University of Washington. And Carrie, you should have control over my slides, but there might be a little bit of a lag.
Okay, great. Thank you. So my name is Carrie Garrison Laney, and I am mostly concerned in terms of the hub with working on the geologic evidence for past tsunamis. And my work at this time is focused on Discovery Bay, which you'll notice is not part of any of the collaboratories, but the work that I'm doing there is still relevant to the collaboratories that's inside of Puget Sound and also on the Pacific coast of Washington and probably Northern Oregon, because the site I'm working on is really excellent at recording past tsunamis. And I'm using that information to narrow down the ages and sources of the tsunami record. You'll notice this timeline on the right in pink. Those are the age ranges of the 9 tsunami deposits at Discovery Bay. And if you compare it to the blue earthquake age ranges from Southwest Washington, you'll notice right away that there is not a one-to-one correlation there. And so there are definitely other tsunamis represented here besides our Cascadia generated tsunamis, and that's really been my focus. Specifically, the penultimate event before the 1700 event is a bit of a question mark because it shows up in some evidence around Northern California and Northern Washington and Southern Vancouver Island, but is absent from the record along the Pacific coast in Southwest Washington. So I mentioned Discovery Bay, not in any of the collaboratories. However, it's really excellent at recording tsunamis. It's got a shape that tapers down and really focuses tsunami energy. We know that Cascadia tsunamis have no problem getting in there. You can see some screenshots on the right from the Washington Geological Survey's animation. You might be able to just barely see in the lower panel that the Discovery Bay, which is circled in white, really lights up with Cascadia modeled tsunamis. And we also have a tsunami deposit from Alaska 1964 there. And so that raises the question of how many of these are from local sources and how many of these are from distant sources. So refining this information is going to be able to help us potentially do some things like identify rupture patches. Maybe this event, this penultimate event, is from a shorter rupture of Cascadia. We just don't know the answer to that yet. And there's a lot of work going on right now. There are right now, we're waiting for some new radiocarbon ages, which are going to be used by students Emma Sullivan and Elizabeth Davis at University of Washington. Are going to be working on age models that'll really help narrow down and improve some of the age ranges for the events here. Like you can see a graphical example of what that looks like on the bottom. Also, a study I'm really excited about is a comparison study of the Discovery Bay tsunami record with Port Alberni with Jessica Pilarczyk at Simon Fraser University and her students. And this is going to be really informative because Port Alberni is going to record Pacific generated tsunamis, both local and distant. but is highly unlikely to record any of our crustal fault tsunamis that may have been generated, but that will probably show up at Discovery Bay. And kind of building on to that, I've got some work planned with Yang Wei from the NOAA Center for Tsunami Research. He's also a hub researcher you'll hear from in just a little while, looking at testing some different fault sources for some of these Puget lowland faults, and also a Fraser River Delta collapse, and also Alaska source models to just kind of
30
test
seconds
at Discovery Bay. And this is all kind of like tiny steps that will eventually lead to some more information about our tsunami hazards and timing of them. And I guess my main question for the group is, working on some of these different potential sources, I'd be really interested in getting some agency feedback on how to prioritize these. I have some of my own ideas, but I know that some of our agencies are really interested in some of these other sources to improve the information that they're sharing. And with that, I'm finished.
Great. Thank you so much, Carrie. That was great. So folks, now we're going to take about a minute to go over to the Miro board and provide some feedback for Carrie, either on these questions here or anything else that you thought of during her talk. So the link to the Miro board is in the chat, and we'll go ahead and give you about a minute or so to enter your thoughts there. And if any of you are not in the first session and are having trouble with the Miro board, feel free to message Allie and she can help you out. Okay, so now we're going to move on to our next talk, which is going to be given by Randy Levesque at the University of Washington. Randy, you should have control over my slides, but there might be a little bit of a lag.
Okay, thanks, Erin. Yeah, so I'm going to talk about some of the tsunami modeling work that's been going on, just a couple of projects that are most related to the COPE Hub research. Lois Adams is here with me. I think Dan Cox and Frank Gonzalez are also on the call. So we've been doing a variety of things, but one thing that we are focusing on for the COPE Hub is using some of these new ground motions that Erin talked about as sources for tsunami modeling. In the past, a lot of our tsunami modeling has been done using what's called the L1 event or other events that were developed specifically for tsunami modeling, which were often just static uplift of the seafloor. More recently, we've also been working with Diego Melgar at the University of Oregon on FakeQuake software, which allows us to generate dynamic earthquake models. This animation, if it runs here, let's see, shows a dynamic rupture that starts in the north and propagates towards the south, and the tsunami that's generated by that. What we want to do in the future is take some of these ground motions that were developed specifically for the seismic work and also use those as tsunami sources. And that will help us to do more probabilistic hazard assessment and also look at sort of the relation between some of the probabilistic seismic hazard assessment that's been done in the past and probabilistic tsunami hazard assessment, and try to make these a little more coherent with each other. Initially, we'll be looking at the Cascadia Subduction Zone, but ultimately we'll also be looking at crustal faults, particularly in Puget Sound, Salish Sea. Also, in the past, we've typically only used the vertical uplift over long time scales for the tsunami generation. Horizontal ground motions can be important, especially the sort of the more rapid shaking that can lead to seiching in harbors and in lakes. And some areas may be actually the major cause of a tsunami. Areas that are protected from the outer coast or isolated lakes, seiching could be a significant effect that hasn't been modeled all that much in the past, but that's something that we're starting to work on and would be anxious to get some feedback on whether that's of interest to some of the stakeholders as well. So the other project I'll briefly mention is looking at modeling debris or particles being carried with the flow. This simulation here is actually just passive particles that are moving with the velocities that come out of our two-dimensional tsunami model. This is the downtown Seattle waterfront, the Duwamish area. There's some large container ports here. There's the sports stadiums here. And let's see if we can get this to flow. This is a Seattle fault event. So within a couple of minutes after the earthquake, you see very strong motions here and inundation of much of the onshore regions, including these large container ports. Again, this is just passive particles being carried with the flow, but one thing that we're working on quite a bit is now trying to couple this in with adding mass to the particles so they're accelerated by the flow in a more realistic manner, adding some grounding depth so that if they get into shallow enough water, they stop moving. But you can see quite a bit of interesting effects here in these simulations already. And there's a lot of work being done at Oregon State by Dan Cox and others there on trying to also look at probabilistic models for how debris is distributed, looking at some range of possible earthquake events. One other thing I wanted to mention here was that we often use bare earth topography for doing tsunami modeling. And in many areas where there may be small, not very sturdy structures, that's justified by saying that those structures may be washed away anyway. So it's reasonable to do your tsunami modeling on bare earth. But in an urban environment where there's large buildings that are much taller than the tsunami depth and sports stadiums and things like that, that will not be washed away, then those structures can channelize the flow and you get much stronger flow moving up some of the streets, for example. And so this kind of simulation in the future, we hope to augment with more detailed models of the built environment as well. And then also these two-dimensional models could feed into three-dimensional models of the actual infrastructure involved. So I'm about out of time, but let me just go on to a couple of questions for the stakeholders in terms of this debris modeling. We're interested to get some feedback on what sort of questions or products would be useful, both in terms of immediate life safety or search and rescue, but also in terms of long-term recovery, for example, estimating the quantity and types of debris that would need to be removed in the long term. And then again, we're also interested in potentially modeling tsunamis in lakes or harbors from seiching and are wondering if there are particular locations that this would be of interest to our stakeholders or any other needs that people have that we haven't been meeting in terms of tsunami modeling so far. So I will stop there.
Great. Thank you very much, Randy. So let's go ahead and again, we'll take a minute. If you can keep these questions in mind and go over to the Miro board and provide some feedback for Randy and others, we would appreciate it. We'll take a minute to do that now. And remember, if for those of you that are just joining us, the link to the Miro board is in the chat, and we are happy to help if you're having trouble with that. All right, so we're going to go ahead and move on to our next talk in this session, which will be given by Haizong Wang at Oregon State University. And so Haizong, you should have control over my slides, but there might be a little bit of a lag when you click.
Excellent. Thank you, Erin. Thanks, everyone. Good morning again. My name is Haizong from Oregon State University. I'll be sharing, some of the agent-based tsunami evacuation modeling that we have been doing through the Hub project, and also before the Hub through a series of NSF-supported project. And I apologize for those of you who have seen some of the slides for the repetition. Trying to advance the slide, but somehow, okay, here, see. Okay, excellent. For the purpose, really we wanted to, we have developed, a community-specific type of agent-based model. And what we are trying to use the model is, one on research side, focusing on social technical questions. But on the other side, we're also using these type of models, for community outreach, community education of hazard literacy. And somehow I don't have, oh yeah, now I can, yeah, please, thank you. So I was just trying to activate the video. Not sure if it's
I can do it for you.
Yes, please. Yeah, so what you are seeing over here on the left-hand side is a recorded video from the 2011 the Tohoku event, where I've used this short video for a purpose of just looking at the multiple interacting systems and the components for the hazard, the earthquake and the tsunami, and the inundation, and also the users you're seeing, the people that are using the system, and also the built environment. We predominantly focus on transportation network. So on the right-hand side is, actually an agent-based model that we put together. The agents we're talking about is the users. They could be walking on foot. They could be also using other modes of transportation. So when we started the simulation, that's when the earthquakes happened, and then we're seeing, there are people that are evacuating, but in this model, we are not incorporating the earthquake damage to the transportation network yet. So you are seeing that the yellow dots on the right-hand side, which are the city decks and tsunami evacuation shelters. And so you are seeing also, there are some kind of a bottlenecking type of effects in the simulation that are seeing people are using, the transportation network to access the evacuation shelter. And now, so we're using this agent-based model to couple the people, the users, the hazard, which are seeing the tsunami inundation, and also the built environment, which is the transportation network. Essentially, we can also integrate building as well, and other infrastructure. So this is when I mentioned about the agent-based model, this is a model that we are creating that for research purposes, and also for community outreach. So what I want to do, so on the in terms of the focus, geographic focus, that I'm using a few figures that actually, this is from 5 communities on the Cascadia Subduction Zone. For the Hub project, we have actually collected data from different communities supported in the past NSF project, and also ongoing as well. And from, for example, California, Eureka, California, Crescent City, and in collaboration with Dr. Michael Liddell from University of Washington, and collecting, also getting the data from him in terms of Commencement Bay, and also some of the other communities, Coos Bay, that we have collected. What you are seeing over here is the 4 different components of the evacuation time estimate. But for tsunami evacuation, because there isn't really, other than the ground motion, there isn't really a formal warning. So there is, that manager or the community leader's decision-making time. It's, that is, the ground motion is probably the only warning that the community people are getting.
30 seconds.
Yes, this is some of the community that we're focusing on, but in terms of the outcome, that currently we're working with a group of students, developing a tsunami app. That this app is, will be used for drill purposes, And also that's on the physical drill that people are using the app. And also we are working on virtual reality, just basically building that virtual reality function. Eventually we're hoping to create like a drill equipment, like a trailer that with the virtual reality type of equipment that it can move and from one community to the other. So that will be used for hazard literacy, and this is actually an idea with Alzia Rizzo and a few others on the NSF project. And last but not least, currently in terms of the development, we're focusing on the app. We're hoping to use the app in the winter and the spring, the quarter, and for selected community on the Oregon coast. I guess I'm probably running already out of time.
Yeah, your time is up. Sorry.
Yes. Yeah, I can stop here. It's really short. Sorry.
Great.
No
Thank
worries.
you very
Thank you.
much. Okay, so we'll direct people over to the Miro board to provide feedback for Haizong. We encourage everyone, so both folks, our agency partners and COPES Hub folks, to please go over to the Miro board and provide feedback. And we'll give you about a minute or so to do that.